to the College of Engineering and Computer Science. My name is Michael Georgopoulos. I'm the interim dean of the college. And we are very pleased today to host the Senior Design Day with over 80 projects being exhibited in the Engineering 2 atrium, which is the atrium outside, as well as the Harris Engineering Center, which is the building across. And there are more than 380 students who are participating in the Senior Design Day today. The college's Senior Design Day today is the 5th annual UCF CECS Senior Design Symposium on Renewable and Sustainable Energy, sponsored by Progress Energy, and the college-wide 2013 Senior Design Showcase. Senior Design Day highlights the next wave of engineering, computer science, and the graduate talent in the college. Please visit with the Senior Design Showcase outside in the Harris Engineering Center to see what our students have done. Today's proceedings are going to be available on YouTube after the end of the symposium. A very special thanks goes to Progress Energy, which has been the symposium sponsor for 5 years in a row. Duke Energy and Progress Energy have recently merged to create the new Duke Energy, the nation's largest utility. The combined assets and expertise will help Duke Energy achieve more efficiency to deliver affordable, reliable, and clean energy to approximately 7 million customers today and in the future. In addition, I would like to extend my thanks to EnviroBright, which is our Senior Design Showcase sponsor. EnviroBright was founded by 2 UCF alumni and has evolved into a successful and innovative energy-related company. EnviroBright's mission is to achieve 2 goals: to save people substantial amount of money through use of energy-efficient products and to help our environment. It is my honor today to have as our plenary speaker Ms. Bobby Garrett. Ms. Bobby Garrett is the Deputy Laboratory Director, Strategic Programs and Partnerships for the Department of Energy National Renewable Energy Laboratory located in Golden, Colorado. Ms. Bobby Garrett has focused her career primarily on the interactions amongst technical, business, social, and policy systems as new technologies advanced from concept to commercial application. She has managed organizations, programs, and functions that address technology development and application in the energy, defense, and healthcare sectors for both government and commercial customers. This has given her a broad perspective on markets, emerging technologies, and the viable pathways from laboratory research to marketable products. In her current role as a Deputy Laboratory Director, Strategic Programs and Partnerships at the National Renewable Energy Laboratory, she serves as a member of the executive team that sets laboratory strategy, oversees mission and execution, and laboratory operations, and stewards core capabilities. Ms. Garrett's specific responsibilities include strategic planning and program development, oversight of energy analysis and international programs, as well as programs conducted for the Department of Defense and Department of State. She also oversees the laboratory's public affairs, communications, and technology commercialization functions. Prior to joining NREL in 1998, Ms. Garrett held a variety of line management and program leadership positions at the Pacific Northwest National Laboratory in Richland, Washington, where she had the opportunity to lead research efforts in energy, environment, defense, and healthcare for both government and commercial customers. Ms. Garrett has a BS in Chemical Engineering from Montana State University and an MBA from the University of Washington. Please join me to give a warm welcome to Ms. Bobby Garrett.
Well, thank you very much for that kind introduction. It's a pleasure to be here at UCF today and be able to join you in this Senior Design Symposium. I'm really looking forward to seeing all the projects. What I want to talk about today is the challenges that we face as a nation and as a globe relative to our energy systems. I'll talk a bit about that. I'm going to cover some background on energy. I'm going to talk about some of the emerging trends that we see in technology that are offering some exciting possibilities in terms of how we will transform our energy systems over the next several decades. And then I'm going to bring it back to what we're doing at the National Renewable Energy Lab very briefly, and then close up with some remarks on career paths. So let me start with the challenges that we face in energy. Our current systems for how we use energy, produce energy, and move energy are not sustainable. If you care about the, climate change, if you care about affordability and reliability, it doesn't take very long working in this field to know that we need to change. And we need to change in a direction that will be sustainable over time. And that requires that we look at all energy pathways and develop systems that can address the diversity of those pathways in systems that are affordable, accessible, and when I say accessible, available to everyone. There's still 2 billion people on the planet that do not have access to electricity. And in order to support economic development in those countries where they don't have access, we need to take a different approach than we've taken in the developed world. We need to secure our energy systems so that they can withstand the threat of cyber attacks or physical attacks. And so it's very complex issues that we're facing. We need to put all of our resources to their best and highest use. We have a scarcity of resources in some respects, and I'm not talking just about energy, I'm talking about water and land use as well, because all of those get affected by the way that we develop our energy systems. Whoops. Well, technology can sometimes be a boon or a bust. So while you're doing that, I'll keep going. The very first slide that I wanted to get to, here we go. Okay, now I'm trained. Talks about how we consume energy at the global level. If you look at this pie chart, what you see are the carbon-bearing sources of energy, fossil fuels. They dominate our current consumption of energy. The non-carbon bearing, for the most part, fuels comprise about 20% of overall use. In the renewable world, the one in which I work, about half of that actually is carbon bearing. This is traditional biomass, burning biomass to create cooking heat or to heat homes. And then we've got what we call the modern renewables that comprise 8 or 9% of our overall use. These are the emerging technologies that really have been growing on a very rapid pace globally over the last couple of years. Wind installations and solar installations globally have paced anywhere from 30 to 60% on an annual growth rate in terms of new capacity additions over the last many years. And you can see some of the leading countries here. This is actually a slide that's focused just on electricity capacity, not electricity and fuels. But you can see across the board who's leading in terms of installed capacity in various areas, country by country. I will say that China's coming on strong in all of these areas. They've made very strong commitments to a development path that's inclusive of renewables, and they've created a manufacturing base there, so we're going to see a lot more probably movement in the leadership positions as we go forward. If you bring that down to the United States, we're not too different from the profile that you see on a global basis, still dominated by carbon-bearing fuels. At this point, we do use more nuclear power in this country than you see on a global basis, and slightly less renewables. The renewable growth in the rest of the world, as well as here in the United States, has been largely driven by policy measures. In some cases, particularly in the European community, that's been an industrial policy or job creation policy, if you will, around trying to create new businesses and have those businesses not just support renewable development in their own countries, but also be an export market to the rest of the world. And then some countries, it's more about needing to sustain their energy systems because they're net importers of energy from the rest of the world. And you certainly see that in Japan as an example, where they're totally dependent for the rest of the world on the energy resources that they use. Here in this country, we've had kind of a mixed policy envelope, if you will, kind of starts and stops at the federal level, but at the state level, pretty strong commitments through renewable portfolio standards to help drive these new technologies into the marketplace. But with that said, in order to have sustainable solutions over the long run, we need further development in these technologies so that they can stand on their own without incentives in the marketplace be economically competitive with the alternatives. So here's the big wild card that's out there in the market right now, and that's low-cost, unconventional gas, if you will, shale gas. Over the last couple of years, we've seen a significant increase in the production of low-cost natural gas. It's already affecting the market in very significant ways. In the electricity sector, what you see is new capacity that's coming online, being largely natural gas, still some renewables, but largely not coal at this point. And we're seeing retirement of some of the older coal plants that have the larger emissions profiles and the turn to gas. We also see some fleet turnovers, largely heavy-duty vehicles turning to natural gas because of the low cost. Where this will end up, we don't exactly know at this point. We imagine, if you have an economics background at all, that the price of natural gas will equilibrate with the global market, because the prices we have here in the US are much, much lower than you see on the global market. So that will become equalized at some point. And what that will do in terms of what I call our race to gas at the moment is a big question. Now, one thing I'll say about our energy future is, if anybody thinks there's a single silver bullet that's going to solve our energy problems, that's not the case. What we're going to see is a variety of solutions, and what's really important is how do all of these energy resources and technologies work together synergistically in systems to deliver the kind of attributes of the system that we need as we go forward: clean, affordable, reliable, secure. This is just another graphic that shows what's been happening in the electric sector in terms of new capacity additions. You can see the rapid growth in gas, kind of, and the decline in coal in particular in this graph. So I want to talk a little bit at this point about, so what are some of the emerging things that are happening, but to set that context first with a couple of studies that we completed at the National Renewable Energy Laboratory in the last 6 to 9 months. One of those was called the Renewable Electricity Futures Study. We conducted this study with 120 researchers throughout the country and about 30 institutions. And what we were looking at is what happens as you move to ever greater levels of renewables on the electricity grid. And we ran scenarios that went all the way from 20% renewables, which is still higher than what we do today, up to 90%. And our question was around where does the system break down as you move to higher levels of renewables? And what can we say about resource availability and how you operate the system, and what does it cost? The major findings of that study, interestingly enough, found that we have adequate resources in this country to provide up to 90% of our power on an hourly basis in every region of the country. So we have no resource scarcity when it comes to renewables. Secondly, we found that if you were to move to high levels of renewables, well beyond what we experience today, we have operational challenges in how we manage the grid. But we have a lot of options for dealing with that dynamics of intermittent resources that range from how you address the demand side, dynamic loads, to storage, to wider balancing areas. There's a whole toolkit that's out there, but it still will be challenging, and we need new innovation in that area. And finally, I'd say, with respect to cost, it will cost more. Any low carbon solution is going to cost more than today's system, and that's because we don't internalize the cost of carbon in our system today, but the cost of a renewable future is no more than a cost of a carbon capture and sequestration solution on the fossil side or a nuclear side. So we're in the bounds of all future scenarios. But with that said, there's a whole lot more engineering improvement that can be done to drive down the cost of these technologies, and that's what engineering's about. We also did something similar on transportation. We looked at transportation energy futures in conjunction with the Argonne National Laboratory that's in Chicago, Illinois, and again, a national team looking at what are the options for reducing carbon from that sector. All of these studies show the possibilities. All of them bring maybe down to a fine point that the biggest lever that we have in terms of creating any of these futures is innovation in technology. And innovation of these energy systems requires a broad set of engineering and computer science skills. So I'm going to talk very broadly about some trends in 4 broad areas: mobility, electricity generation, energy efficiency, and maybe my current personal passion, which is systems integration. So for sustainable mobility, the kinds of things that engineers are working on today go from the demand side, so looking at how do you make the most efficient vehicles as possible. So even if they're continuing to operate on gasoline, they're getting the most in terms of miles per gallon out of the gasoline. That's including some exciting work in lightweight materials. The more weight you can get out of the vehicle, that's probably the highest lever you have in terms of high efficiency. But across all the systems, combustion, improving the combustion efficiency, new engine designs, and in this case, electrification of vehicles. We believe that the future of vehicles they'll all be electrified to some extent, either in hybrids that use batteries and conventional gasoline engines, but those engines could be fueled with biofuels, or it could be a hybrid with a fuel cell, or a totally electrified vehicle that gets recharged. Now, most people have a mental barrier to buying a vehicle that has only an 80-mile range between charges. That's a huge area of research where we need to increase the miles that you can go in an electric vehicle to at least 300 miles to be compatible with current system to get over the barrier that the consumers face. Some of the work that we do at our lab involves dealing with the auxiliary loads in electric vehicles because they become very important. They're draining electricity out of the system to heat or cool the passenger compartment. And so totally new designs, because you don't have the heat of the engine anymore to heat the passenger compartment. So new heating and cooling techniques are needed. The other side is dealing with biofuels, advanced biofuels that can replace gasoline. We've actually this last year demonstrated cellulosic ethanol can be cost competitive with gasoline once you built the nth plant, not the first plant. But that's also going in another direction at this point, which is to look at higher density biofuels, fuels that can be used in heavy-duty vehicles and airplanes. And of course, ultimately, hydrogen fuels that can be used in fuel cell vehicles. Sustainable electricity generation has been the core of our laboratory for a long time, and not only our lab, but many institutions, universities, and other labs throughout the world. We're seeing at this point large-scale solar systems coming into the grid. We're seeing, happens to be a picture of an offshore wind farm. This is off the European coast. What you're seeing here, it's a foggy day. This is a beautiful picture of the flow effects in a wind field. What happens is every turbine that's behind a turbine sees a flow effect that's different because the turbine ahead disturbs the wind. This is a whole new area of research, understanding those dynamics in wind fields, because depending on how the wind blows and how you design the field, you're either optimizing the performance or you're reducing the performance. So a brand new opportunity to understand that better, and that's what that visualization was, is a computer simulation of the aerodynamics in those wind turbine fields. Marine hydrokinetics is an emerging area worldwide, particularly important to island nations that are most susceptible to raises ocean, increases in the height of the ocean as we warm the climate. So this provides some no carbon solutions for power. Geothermal energy, this has been the workhorse in many ways in the U.S. for baseload power from the renewable fleet, but largely limited at this point to the south and the west where the hydrothermal resources reside. But the direction of the research is to make that more broadly available across the U.S. By drilling deep into the earth, creating a reservoir that and then pulling the heat from the earth through fluids to the surface and running that through conventional generators. So that's a long-term research effort to engineer those systems. A lot of opportunity there for research and engineering going forward. On the energy efficiency side, we often talk about this as the vast near-term untapped potential throughout all of our engineered systems, our built environments. There's a lot of exciting things happening in terms of both component technologies as well as the way the systems are being brought together. Some of the things that you might hear a lot about as we go forward, already emerging into the market, solid state lighting. Significant opportunity to continue to improve that technology as we go forward and to engineer it into systems that can be introduced not only in new designs but also in retrofit. Retrofitting buildings is the big untapped potential that represents the vast majority of where we use energy today. Another materials area is electrochromic windows that can change color as the sun rises or sets. This happens to be in the office building I work in, and we see that change throughout the day. It reduces the heat load in the building. This is actually the building that I work in. It's the largest net zero energy building in the world. It houses 1,300 staff. It produces as much electricity on an annual basis as it draws from the grid. That's because of its extremely efficient design. We've about halved the energy footprint of the building on a 1,000 BTU per square foot basis through good engineering at no additional cost. So when there's a will, there's a way to get this done. We have the existence proof that it can be done, and it can be done in a commercially viable way. It's how you think about and how you integrate the technologies into a system that can operate with optimal performance. And that lower picture is the whole building. What's also interesting and something that we don't always think about is that humans are part of these systems. And so what we do in our building is we have an interface on our computer system. So each desktop has a little app that tells you how to interact with the building. If you're too hot or too cold or the lighting isn't quite right, it's too humid, you have a place to enter that information. So we know both through all of the sensors throughout the building as well as the human inputs, what's going on with the building, and it changes how we operate the building, and we're learning a great deal from that. You get signals on when to open or close your windows, so it's quite an interactive process, and we're learning a lot about how much human behavior is a big factor in the overall energy efficiency of the building. So I want to now bring it to really an exciting emerging area, which is energy systems integration. And I kind of played off of that when I talked about the building, because this is about how do you design and then operate systems to get the maximum performance attributes that you're trying to reach. This has kind of been an underemphasized area because we kind of think in disciplines or we think around individual technologies, but there's a lot of untapped potential in how you think about bringing things together into these larger systems, whether they're fuel systems, electricity systems, or thermal systems. And when you start to think about the trade-offs and the optimization that you can do across those pathways, both in the early design, but also as you operate systems, you can wring more efficiency out of the system, if you will, reduce more carbon. But what's required to do that is to think across scales that go, I'll use electricity as an example, go all the way from plug loads to national grids and have toolkits that allow you to manage the system of systems with knowledge, if you're in a building, of what's happening on the grid, or if you're at the grid level, what's happening at the plug load or the building level. Right now, our systems are not particularly smart, so a key to being able to have greater insights into how the systems operate and how to optimize them is information technology. So this is really marrying information technology and engineering together in ways that we haven't done up to this point. You've heard of the smart grid. That's a good example. That's involving the consumer, the building, and the utility in a continuous system and in terms of how it interacts to derive greater efficiencies and greater affordability for the customer. That's the intent. So one of the new and exciting things at the National Renewable Energy Lab is a new facility that we just completed construction on. And the whole purpose of this facility is focused on energy systems research at a scale that makes a difference in the commercial world. There's a lot of other capabilities, both at our lab and elsewhere, that are at a smaller scale, and those are important to be able to conduct what I would call bench scale experiments. But particularly when you're dealing with utilities, they're very risk averse. They don't want to put any new technology on their system unless you've gone through some very rigorous testing to be able to prove the value of that technology, and to be able to show, okay, if I do it in one place, but then I replicate that across my system, what does that do to the overall system dynamics? So that's what this capability is going to be able to do. And in the heart of this capability is a high-performance computing center, and that's linked to our laboratory, a lot of high bay labs that allow us to connect individual experiments to replicate systems. So you can imagine in one lab we might have a fuel cell running, in another it might be a battery bank, and another outside test pad we might have photovoltaic cells. We could have diesel engine generators, and you can connect those in a microgrid and collect real-time data. And using that real-time data and understanding the dynamics of systems, then we can develop better interfaces and controls within the system and optimize those configurations as we go forward, and also be able to visualize through modeling what the impact if you deployed such systems at scale on a particular grid. So the concept of operation is to have the actual running experiment, the test article, streaming real-time data, using that data to mine the information value about the interfaces and how the system operates and the dynamic configuration. Use that to improve our understanding of the systems so we have better models in the future. And as a result of that, better control and interface systems. And you can imagine that the users of this capability will not only be the scientists and engineers that operate in a research community, but the suppliers, for example, to the utility industry. They can bring their prototypes when they're still in the design stage in CAD/CAM system and test run their designs in this hardware-in-the-loop system in a virtual sense before they reduce it to a prototype. Then once they have the prototype, they can bring it in and actually test it in a grid-simulated environment so that they can shake the issues out of their prototype before they ever go to manufacturing. So this helps accelerate the process of moving from innovation to actual product and reduce the cost and the risk of scale-up of those products. Then on the user side, it allows the utilities, for example, or large campus energy managers to experience the technology before they ever put it on their system. This is just an example. This is actually a project that we're doing in the field with the Sacramento Municipal Utility District, where in this subdivision there's houses that have been built with about 2 kilowatts of photovoltaic arrays on the roofs. Some of these have solar water heating systems. Some of these have electric vehicles. And so we are gathering data on that distribution feeder within that subdivision to understand the dynamics that are occurring within that particular distribution system. We're able to model and visualize that within our facility. We're testing some new inverters that can deal with the voltage sag that we're measuring out in the field. And then we can model, okay, so if we actually installed that new inverter on the feeder, where should it be installed, and what benefit will it have in terms of dealing with the voltage sag issues. So I've talked a little bit already about what the National Renewable Energy Laboratory does, but let me bring that back to some high-level points. We are a Department of Energy national laboratory, one of 11 national labs. We're the only one that has a very focused mission advancing renewable energy and energy efficiency technologies and moving of the electrons and fuels and thermal energy from where it's generated to where it's being used. So all of the physical assets of the lab are owned by the Department of Energy, but the lab itself is operated by a limited liability corporation called the Alliance for Sustainable Energy. This is how most of the national labs are operated. We have about 2,400 staff on site. About 1,700 of those are payrolled staff. The others are come to us as student interns, joint appointments from universities, postdocs, or other temporary staff. So we have a very dynamic workforce. We're always eager to have student internships, and I'll talk more about that in a moment. We have had the benefit of having a lot of investment in new facilities at our site over the last 5 years. I talked about the Energy Systems Integration Facility and our large office building that's net zero facility, but we also have facilities for pilot scale production of biofuels. We have an alternatively fueled fleet that we use to move people and supplies across the campus, but it's also a research tool. We're instrumenting all of those vehicles and gathering that data. We have 2 sites. One of those is our National Wind Technology site, where we have megawatt scale turbines from the commercial industry that comes in. We do experiments on control technologies, on new blade designs, on new turbine designs, tower systems, the whole gamut. And what's most important, and what kind of resonated with me in my visit here with some of you yesterday, is we're not successful at our laboratory unless the knowledge and know-how that we develop gets out and gets used in the commercial marketplace. And so on an annual basis, we have about 350 partnerships with commercial companies, both domestically and internationally, and with all branches of our government. We're working with Department of Defense, Department of State, Department of Interior, EPA, Department of Homeland Security, all on helping them implement energy systems that can be more sustainable, more secure. And our campus is a model for sustainability. We're very passionate. We can't be credible in the world around the energy systems that we're researching unless we use them on our own campus. And so on our main site, we generate about 1/3 of our electricity on site, either through a biomass heating plant that's displaced our natural gas use, or through on-site renewables, largely photovoltaics. Because we're land limited, we can't produce all of our energy on that site, so we purchase renewable energy credits to offset what we purchase from the grid. So we're a net carbon neutral site. At our wind technology site, we're producing 3 times as much energy as we need at that site, and so we're exporting that to the grid. And we've turned our campus into a research tool. So it's not just a statement of how to use these technologies. We're gathering data off of every end use and every supply system. And that's a whole new area of research, big data, second data off of energy systems. How can you mine the information value out of that data? How do you visualize what's happening in these dynamic systems? and consequently, how can you improve the operation of the systems. In terms of our research portfolio, we work on residential buildings, commercial building, energy efficiency technologies, personal and commercial vehicle technologies. And we work on every renewable energy form, if you will, except for conventional hydropower, for whatever reason. There's other labs that do that. And again, we work on how you move energy from where it's produced to where it's consumed, or how you store energy, an increasingly important aspect of research. And again, we are aimed at markets that are national and global in nature. We're working right now in about 74 different countries, just to give you a sense of our reach. I talked a little bit about the sustainable campus already, but the people that come to work at our laboratory are absolutely committed to this vision of transforming energy systems so that they can be more sustainable. We know we have one tool in the toolkit. It's not the only solution. It's got to fit with all of the other energy pathways. And so that's why I put a particular emphasis on systems research, because it's all about how you use these things together. So let me talk just very briefly, offer some perspectives on careers in energy. This is very NREL focused, but I want to make a couple of points with this. One is whoops, sorry about that. One is that our opportunities at the laboratory go all the way from basic science through market relevant applied research to testing and validation. This testing and validation is not only for our NREL originated technologies, but the industry comes to our laboratory to bring their prototypes, and we test and validate the prototypes for the industry, the wind turbine manufacturers, the PV panel manufacturers, the catalyst developers for biofuel systems as examples. And we provide them with very important information that helps reduce their risk and improve their technologies before they spend a lot of money on them. We commercialize the intellectual property of the laboratory, but then we don't stop there. We can't transform energy systems unless those that are out in the marketplace can use them. So that we work on what we call deployment, which is reducing the barriers to their widespread adoption. This could be helping standards bodies develop standards for new technologies that don't exist today. In some cases, it's providing information to those who are trying to make investment decisions. Sometimes it's our own federal government. What technology should they use at a particular DoD installation if they're trying to secure the energy systems at their facility? Or it's even the investment community, informing them on what the trends, emerging trends are in technology and where the opportunities are for investment. Down the right-hand side of this slide are just a set of core capabilities. These are not all the capabilities of the laboratory, but they're some of the ones that are perhaps most prominent. Perhaps one that I didn't list here that should be here is high-performance computing. Computer science is probably embedded in all of these others. It's a very important aspect of what we do and will be as we go forward. Did you catch the tagline at the bottom? That's the link to our jobs that are posted on our website. I didn't point to that, but that's, if you're interested in looking at either permanent careers, student internships, postdoc opportunities, they're all posted here. And I would encourage you to check multiple times. It's very dynamic. So what's there this week will change by next week. So I wanted to just say a couple of perspectives from where I am in my career. I'm a chemical engineer with a business degree. And what I would say is that when I started my career, I had no idea where I would end up. In fact, I kind of stepped into engineering without even knowing what it was to start with. I got my degree in chemical engineering with the thought at that point in time that when I graduated that I would be going to work in the petrochemical industry because that's what the training was about. I chose not to do that. I actually started my first job in nuclear waste cleanup. And why did I do that? Well, well, I guess maybe I'm motivated by the things I don't know and that I want to know more about. So when that opportunity presented itself to me, I thought, well, I don't know anything about this. Here's an opportunity to learn something new, so I jumped into it. During that time period, it was when we were starting as a nation to make serious investments in renewable energy. And I happened to become aware of that and realized that nuclear waste was not the career I wanted. So after 2 years in that business, I made a transformation to a different position, which was at a research lab in Washington State. And it was because I was working with some colleagues who were working on nuclear waste, but they were also aware of what else was going on in the research world, and that sounded interesting to me. So I spent 20 years in research and development at a lab in Washington State, and that gave me a whole variety of opportunities. I don't think I was in the same job more than 3 years in a row, and had a whole variety of opportunities, most of which, when I look back on them, were leaps of faith. They were into areas that I hadn't considered. They were presented to me, and I thought, well, I don't know how to do that because I haven't done it already. But I took a risk, and I jumped into something I didn't know about and had a tremendous opportunity to learn. And what I found is that when you're learning, it's some of the most exciting times that you can have. So over there you see learning continuously. That's a rewarding career when you can have that kind of opportunity. And then I had worked in energy projects, environmental projects, defense projects, healthcare projects in my research career. It gave me a pretty broad perspective. I had the opportunity to be a project manager and a line manager, and was presented with the opportunity to join a different lab. And I thought about it. This was probably the point in my career where I thought, I've got to really follow my passion. And my passion is about transforming energy systems. Again, I think it's the biggest challenge of our time, and I wanted to make a commitment, go to a laboratory where that was their sole focus, not just a focus. And I made that transition about 15 years ago to join the National Renewable Energy Lab. And what I would say, even in a more focused mission, the variability and change in the topics that we're dealing with is pretty significant. And I often tell people I have the attention span of a 2-year-old, so I like a lot of variety. And this gives me that, and I think that's what attracted me to the research field as well. So when people ask for career advice when they're making critical decisions at junctures in their career, the things I say are follow your passion. If you follow your passion, everything else tends to fall in place. If you demonstrate commitment in each role that you take on, more opportunity will come your way. Be open to change. Don't be afraid to take a risk. You don't have to know everything on day one. You're going to learn as you take on different careers, so don't be afraid. Take every opportunity to learn. You're doing that now, obviously, by committing to an engineering education here, but that never ends. You learn a tremendous amount in the workplace. Most employers also offer some support for continuing education, and we do that at our laboratory. So both through formal processes and on-the-job processes, commit to that learning. Think beyond your scope. I've found when I look at people who are trying to advance their careers or people who did, it's being able to see the bigger picture beyond what you're working on in your immediate scope that helps advance your career. Some of that is working in teams, and that's another theme that I've seen in my visit yesterday and certainly in the way that you're approaching your design projects. So, for what it's worth, that's my career advice to you. And with that, I'll be happy to answer any questions. Thank you. Yes.
With your net zero building, are there high maintenance costs that go along with that? And how long do you think it'll take until that becomes a common thing?
Both good questions. So the question was, do we have high maintenance costs with our net zero energy building? And then how long will it take to get net zero buildings more widely replicated as a practice? So there are not high maintenance costs. It's actually a pretty low maintenance building because what we did, what we say is that when you design such a building, at least our experience in our climate, is that we spent more on design at the front end and less on mechanical systems at the back end. So we don't have a traditional heating, cooling, and ventilating system, a mechanical system. We're collecting, for example, waste heat off of our data center. The distribution mechanism for both heating and cooling in the building is piped water. And so some of those mechanical systems that are maintenance issues, we just don't have those. We take advantage of the dryness of our climate and the heat of the earth. So we have a labyrinth underneath our building where it's either a heat source or a heat sink. We use a lot of day lighting, so we have less lighting in the building, and it tends to be task lighting or very high efficiency lighting. There's not a lot of moving parts. It's very simple. In some ways, it's like going back to the way that buildings were built in the past. We actually, in a federally owned building, have windows that open and close. That's unheard of for the most part. So we're breaking some ground policy barriers. Now, in terms of replication, we built this building using a process that's not commonly used in certainly the government sector, and that's design build. That's when you write the specifications and then you trust that the design build contractor is going to bring you innovation to meet your specifications. We wrote the specifications by using a building energy model, so we were able to say what's the art of the possible. So we set a design energy budget for the building. We said it had to house 1,300 people, and there's a cost constraint. So 3 constraints. 3 of the teams that we asked to bid on the project threw up their hands and said it can't be done. And 2 of those teams were able to coax back to the table along with another team. And one of the ones that walked away originally is the one that built the building. They showed so much innovation that in some cases they exceeded our design specs, and it changed the way that they're looking at their entire business. We've gone through a process of gathering all of the learning from the building. That's all available. We've held forums with other builders to talk about the process. But I'll say the thing that's probably most important, because it's what carries the day in the commercial sector, is that we were able to build this building and operate it at no additional cost beyond what you would see in commercial buildings today. We're actually, on a square foot basis, at the lower end of commercial construction. And when you add the fact that you're saving operating costs because you're using less energy, that's very attractive to people. It's the process that's replicable. You could not pick this building up and put it here in Orlando and get the same performance because you all have a different climate. So it's how do you bring the systems together. So sorry for the long-winded answer, but I get passionate about this stuff. Any other questions? Sure. Uh-huh.
I know that we'll never be able to harness all of the energy that's out there, but are we looking into the long-term effects of harnessing more and more of that? Let's say more and more heat from the earth and more potential energy from wind and tides and stuff like that. What would the long-term effects of that be?
That's a great question. What I would say is every pathway, every energy pathway has consequences, and you need to be very mindful about that, both on a near-term point-of-use basis, but over the longer term. So there are some long-term science studies looking at what happens as you capture more of the wind. What effect does that have on local climates? Same with solar energy technologies. If you deploy at scale, what happens? Also interestingly, there's work being done on the effect of climate change on resources and where those resources reside. Because you can imagine with climate change, you're changing the so many of the Earth systems. So we have to be mindful of that. One thing that I would say is that analysis is part and parcel of everything that we do at the laboratory. We have a strong ethic of doing life cycle analysis on all the technologies that we develop. We want to understand what the consequences are so that we avoid or engineer in the avoidance or mitigation of those impacts as we develop the technology. So they go hand in hand. I think I saw another, yes?
So you had a lot of focus on the system integration aspect, which I think is great. Who are the leaders within industry in bringing those innovations forward?
Okay, so there's several. In fact, one of the partners that you work with is one of the leaders, Siemens. A lot of focus on grid integration technologies. Lockheed Martin is one of those. There's a lot of startup companies as well, smaller companies that maybe their names are not as familiar to you. Spire is one of those. They're working on smart grid technologies. Some of the leading builders now in terms of high efficiency building design are thinking about this as well. Let me think of other examples. Well, IBM, the information technology industries, Google's, the IBMs, are really seriously thinking about the data implications and the informatics, which is essential to being able to understand how to integrate and operate these systems. The more information you can have on a real-time basis, the more that you can optimize the system. Yes?
I noticed from your third chart or so, not every country is concentrating their effort in a particular strategy for generating energy. Are they, or we, using a different formula for the return on investments? Because not all of them are looking at wind turbine technologies. There are various ones and they rank differently.
Right.
Maybe they have, or we have different resources that they don't have, and that's why we're concentrating on a certain aspect of it. Would you elaborate on that?
Sure, yeah, that's a great question. And you've got the answer embedded in the question in two ways. One is there's a considerable amount of variability in renewable resources on a geographic basis. Even here in the U.S., the diversity is quite significant over large land areas, and that's true throughout the world. So it starts with understanding what resources are available to you. Another aspect is how accessible are those resources. And particularly if you think about electricity as an example, if you're in a developing country, it's unlikely that you have the grid infrastructure to move the electricity from where the resources are to the load centers. And if they're not in proximity, that can be a barrier to the way that you develop. So an opportunity there is kind of the analogy to the cell phone is don't think about central station generation, but think about distributed generation and locating smaller distributed generators closer to the load if the resources are there to do that. So, you know, how you build out your infrastructure is an important consideration and reflected in that. Economics is the driver, okay? And so for the most part, as I mentioned earlier, the economics right now on a lot of these systems are being driven by individual country policies. In the European community, kind of in broad stroke, has made significant commitments to carbon reduction. And that has driven the markets in Europe and in individual countries. Combined with carbon reduction commitments, they've also had economic development commitments, and you certainly see that in Germany. Germany doesn't have a very strong solar resource. It's about equivalent to what we would see in Alaska. And yet they made a commitment to feed-in tariffs, which is the purchase power price from renewable technologies that drove photovoltaics into the market. They're some of the world leaders, like the Fraunhofer Institute in photovoltaic research and design systems. And they're a net exporter of photovoltaics. That was an industrial policy that they put in place. because they wanted that world export market. So it's very variable in terms of how the countries are viewing it. Most every country, like I mentioned, we work in about 74 different countries, are pursuing some form of renewables at this point.
You
Yeah.
mentioned policy and you're working with a certain power grid company for some of your research, but traditionally there's always been a lot of resistance to sustainable energy change from the power companies, it seems. And I was wondering if that's still an attitude that's current in our federal government system, or if that's, you still come into a lot of resistance, or if they're starting to kind of give way and accept that the change is going to come.
We've seen a lot of acceptance, a lot of change in the traditional utility system. What they're finding is they're finding business models. Again, they're conservative, so they need the existence proof to be able to experience the technology. And just give you a quick example, and then I'll be quiet. So our own local utility, when we passed as a ballot initiative the Renewable Portfolio Standard in Colorado, it had a solar set-aside. They were already implementing wind on their systems through a green power program, and that meant it was an optional program to pay more on your utility bill, which people did, in order to get wind on the system in Colorado. They didn't know how to deal with solar, and the day after the ballot initiative passed, they came to the laboratory, and we started to help them. Within a year, they had found a business proposition where they could make money from solar energy, and it just went from there. So it comes with experience, and we're starting to see that in utilities across the country. Okay. Thank you.
Thank you very much, Ms. Garrett. Good morning, and once again, welcome to the UCF College of Engineering and Computer Science. I'm Chuck Riley, Associate Dean for Academic Affairs. Our college's Senior Design Day includes both the 5th Annual UCF CECS Senior Design Symposium on Renewable and Sustainable Energy, sponsored by Progress Energy, and the 2013 College-Wide Senior Design Showcase. During their senior year, UCF engineering students bridged the gap between academic and professional experience by participating in year-long design and build projects that push them to the boundaries of their own disciplines and beyond. Along with their faculty advisors, students work to develop innovative and creative product proposals, design and build prototypes, analyze the performance and impact of their designs, and prepare engineering reports. At the end of their senior year, students present and demonstrate their projects at Senior Design Day, where today over 80 projects are on display. Each senior project provides invaluable experiences in project management, entrepreneurship, leadership, social responsibility, and team building. Applying classroom learning to solve real-world problems is something we do very well and often at UCF. This year's Senior Design Symposium and Showcase features great examples of innovation and experience-based learning at its best. Thank you all for being here to celebrate the achievements of the next class of UCF engineers. Before we begin our symposium presentations, I'd like to acknowledge the faculty who support our students in their senior design courses. Will the faculty who are present, who I can't see right now with these lights, would you please stand up to be recognized? On behalf of Dean Michael Georgopoulos, Dr. Ranganathan Kumar, Associate Dean for Research, our chairs, your faculty colleagues, and most importantly, our students, I want to thank you very much for your dedication, your selflessness, and your guidance. Kudos for a job well done. I'm about to introduce our first team. I just want to make a couple of quick announcements before I do that. When the teams are up here, I'm going to ask that you speak from the podium, okay? That's this thing, okay? Appreciate it if you'll do that. And what I'm going to ask the audience to do is to hold your questions for later on when you can visit the teams at their booths and ask them there. And I know there may be some additional questions that some of you have for Ms. Garrett. She's going to be here for a few more hours, and she'll be wandering around visiting some of the booths herself. If you have more questions and you'd like to speak to her again, I encourage you to do that as well. So without further ado, I'd like to introduce our first team bringing solar power to the South African township of Pomalong.
You guys need the music for me? If you want. All right. So, can everyone hear me? Yeah? Okay. All right. So, good morning, everybody. We're Project Helios, and Helios stands for Greek god of the sun. And my name's Corey Bianchi. I'm the computer engineer for Group 29. And our project was to generate a solar power system for South Africa for a township called Pomalong. So our motivation for this project was to acquire international engineering experience, also design a solar power system, to explore new cultures and explore new horizons, as well as to promote the use of new, clean, and sustainable energy sources for humanitarian efforts. So you can see here are some pictures of the Pomalong. Those are some of the kids there, and the township in the back, as well as the picture of the South African flag. So some demographics is that about 38% of the population live in a rural area, and they have about 50 million people, about 10% of which have the internet or are able to use it. Whereas here in America, we have about 75% internet users of our population, and then about 78%, or 78 years they live here as their life expectancy in the US, and 50 years over in South Africa. The unemployment rate for ages 15 to 24 is 48%, whereas here in America it's about 17, and about only 4 out of 5 people are literate, which they can read and write, where here in the US is 99%. They have a negative population growth rate. About half the people live in poverty as of 2000, and here we have about 15%, and about 1 in 5 have HIV or AIDS, whereas here it's about 0.6%, so much less. So where is this located? So if you guys can picture South Africa in your minds, and the bottom part creates South Africa, and then we're going to be flying, or 2 of us will be flying to Johannesburg, which you see up there, and traveling south to Pomalong. I have Harrismith highlighted here because it's nearby, and we were unable to find Pomalong in the Google search. That's how small it is. It's about 2.5 hours away and about 150 miles. So our goals and objectives for this project was to generate, store, and distribute power. We wanted to create a self-sustaining, reliable system, something that was going to improve the quality of the township, and to deliver AC power. And you can also see a picture here. This is the community center where our project will be sent to and deliver some power.
Hello, I'm Patrick. I'm going to talk a little bit about our specifications and requirements for the project. Some of the specifications and requirements included we needed to be able to produce 1,000 watts of power. The input had to be able to handle 30 volts and 32 amps. The output has to be 220 volts at 50 hertz, which is the requirements over in South Africa. The battery bank has to be able to handle 7.5 hours at 10 amps without being charged, and has to be able to operate in temperatures ranging from 0 to 125 degrees Fahrenheit. This is our general block diagram. The solar panels will catch the sun's rays and create electricity, and then the charge controller will be used to manage that energy and store it into the battery banks for later use, and then the inverter will take the power stored in the battery banks and convert it into usable energy. So to talk a little more about the solar panels. Each solar panel will produce 235 watts with a maximum output voltage of 30.2 volts and a maximum current of 7.92 amps. Now to go a little more in depth into the charge controller. The charge controller, the specifications and requirements for that were it has to take an input ranging from 5 to 30 volts, a maximum input of 32 amps, and must deliver a constant output of 20 volts. The main functionality of the charge controller is to take the power from the solar panels, manage it, and charge the batteries.
Good morning, everybody. My name is Estebanos, and I'm going to talk about the battery bank. As you guys can see, our battery bank specifications and requirements are to have 3 batteries, 6-volt batteries in series, so we can actually be able to store 1,000 watts of power. These need to be lead-acid batteries, and they also need to be deep cycle batteries. Its main functionality is to be able to storage DC energy that was produced by the solar panels. All right, now let's talk about a little bit on the inverter. As you guys can notice, here's our specifications and requirements for our inverter. We need to have an input voltage of 18 volts DC so we can actually output a pure sine wave. This output needs to be at 220 volts AC and at a frequency of 50 hertz so we can actually deliver 1,000 watts of power. As you guys can see, that's the picture of our inverter, and its main functionality is to convert DC power, which in our cases will be the stored power, into AC power, which is going to be the usable power, the one that we can actually be able to distribute and use. Some of the challenges that we encountered throughout the semester are divided into technical and administrative challenges. Some of the technical challenges were, for example, being able to drive the gate of the DC to DC converter, being able to create a high power LC filter, and the installation of the system abroad. In the case of the administrative challenges, we found problems trying to get funding to travel to South Africa. Actually, only 2 of us are going to be able to travel over there, and the collaboration with the other groups and the Honors College so we could accomplish this project. Talking about inverter efficiency, we managed to have 76% efficiency. And to do so, we compare the power input with the power output. And when acquiring the 76% efficiency, we find out that we were within the range of 50 to 97%, which is in industry, it goes with the industry and standards. Now, I'm going to present you guys a demo of how our system works. Can you go back and forward again? Yeah. Well, the video doesn't work, but okay, there you go. You guys can notice we have a sinusoidal signal coming out of the oscilloscope with 2 light bulbs working, which shows our system functionality and then how they come off. As you guys could notice, that's our inverter, our box that has inside our charge controller and our inverter. It also has a transformer, and some of the facts that you can see over there is that our system efficiency is of 76% and our battery life is of 7.5 hours. Some of the community impact applications are going to be introduced by Pablo Pozo.
Good morning, my name is Pablo Pozo, I'm the electrical engineer. Let's talk about a little bit about the community impacts and applications that we'll be able to give to this community. So right now, there are nighttime activities and at sunset, and with this system, they'll be able to extend their nighttime activities and they'll be able to watch movies, listen to music, or whatever they desire. Also, another goal was to expand their communication because as of right now, they're disconnected from the world. They have no form of communication. And with this system, they'll be able to have a television and radio to communicate and see what's going on outside their community. And education is real important. As we all know, internet access is very important nowadays, and people can learn a lot from the internet, and there's an unlimited amount of information that can be gathered from the internet. And this is a picture of the township. The picture above is their current conditions, and our goal was to achieve the picture at the bottom. The scaling and uses, we placed two scenarios here. If they use one projector, a computer, and a light bulb, the system will be able to sustain for 2.5 hours. In our second scenario, if they use 5 cell phone chargers, 2 computers, a light bulb, it'll also be able to sustain 2.5 hours. The total cost of our project is $2,536. And stepping stone, we hope that that our project is a stepping stone for other senior design projects to participate in humanitarian efforts and put their skills to work and be able to improve the lifestyle of others that in need. And we want to take the time to thank Progress Energy for sponsoring our project, College of Engineering and Computer Science, the Department of Electrical Engineering and Computer Science for sponsoring our trip, Dr. Ritchie for his support, Mike Tolbane for helping us test our equipment, and of course, Downs College. Thank you.
Our second student team will present kerosene-powered porous media burner for efficient heat production.
Hi everybody, how you doing today? I'm Anthony Teresiano, and our group project was a kerosene-powered porous burner for efficient heat production. As I said, I'm Anthony Teresiano. This is James Wilson, Jennifer Jackson, and John Lundy. Our project design goal was to develop a porous burner capable of utilizing a liquid fuel.
For our fuel selection, we saw that the Department of Defense uses 4.6 billion gallons of fuel annually, which is about 12.6 million gallons a day. You can see from the pie chart that Air Force, Army, and Navy use about 90% of this fuel. The Army and Air Force use JP8 and the Navy uses JP5, which both of these fuels are about 75% kerosene by volume. So we decided to select kerosene for our burner to provide similar enough burn data to lend itself to military applications.
So here we have a picture of an open flame produced by a device that I think most everybody here has used at some point in their life, and it's a Bunsen burner. For the application of producing usable heat, this tends to be inefficient because a lot of the heat produced from combustion is taken away with the reactants, or excuse me, the combustion products. So what we aim to do is utilize porous media to harness some of what would otherwise be waste heat, recirculate it upstream into the reactants, and this would result in a higher flame temperature, leaner operation. So for the same amount of fuel, we're able to harness a little bit more energy. This lends itself to an increase in efficiency and also increased flame stability. We also find a reduction in emissions of carbon monoxide and nitrous oxide.
So as far as application goes, the military would be able to utilize the heat produced from the burner to sanitize drinking water. The CDC has stated that boiling water is the best method for making water safe to drink because it eliminates contaminants often missed by chemical disinfection. So therefore, the burner would provide safe drinking water to soldiers and potentially for future FEMA relief efforts. As for a secondary application, the burner would make do as a space heater for tense and cold climates. The burner size meets the Army's portability requirements and its fuel efficiency is an added plus. The burner could also be used as a heat source to dry clothes when soldiers are not near a large base.
So what you're looking at right here is a picture of the completed burner. This is what we had at the very beginning of our slide. The first point that you're going to notice here is our heat exchanger, followed by the vaporization chamber, mixing chamber, and combustion chamber. So this is a block diagram and it illustrates the flow loop properly. So you can see here we have the hot air inlet. This is where the hot air enters our heat exchanger. We have our cold air inlet, which comes through the outside annulus of the tube. We're heating the cold air from the hot air that's exiting the combustion chamber, and then we're exhausting the hot air out of the system. This is where you would go and utilize the hot air for any downstream energy purposes. And then we're taking our preheated air and forcing it through the rest of the system.
And then the preheated air exits the heat exchanger and enters the vaporization chamber. This is where we're going to be supplying our kerosene into the system. We have a syringe pump that pumps the kerosene through needles dropwise into the stainless steel foam. The stainless steel foam acts to expose the kerosene droplets to the cross flow of preheated air, as well as conducts heat into the kerosene droplets directly, which vaporizes the kerosene fuel and creates a mixture. This mixture goes through the mixing chamber that has baffles, which will aid in mixing and produce a uniform mixture, exiting the mixing chamber and being supplied to the combustion chamber.
So here we have a cross-section of the combustion chamber. It's composed. Here we have a cross-section of the combustion chamber. It's composed of stainless steel. This is the portion of the flow loop that contains the porous silicon carbide, pictured here. Another thing to note about the combustion chamber is the addition of thermocouple ports. This allows us to track the centerline temperature during combustion. So as Jennifer noted, the homogeneous fuel-air mixture enters the entrance of the combustion chamber, where it meets the first of two flame arresters. This is a higher density porous material, and it acts to prevent the flame from propagating upstream into the mixing chamber or blowing past the combustion chamber and into the heat exchanger. The next section is where we house our porous silicon carbide, where we'll actually sustain combustion. After the combustion process completes, it exits the combustion chamber and enters the heat exchanger, thereby completing the process.
So now we have a short video of the burner in operation.
Go back one more.
So we have a short video of the burner in operation. As you can see, we have an arrow indicating the direction of flow. So we're flowing from the right side of the screen to the left, and on the bottom we have a scale bar showing the entire length of the combustion chamber. That's not playing. It is? Okay. So as you can see right now, we have the flame as it's expanding out of the combustion chamber, as it's expanding out of the downstream section. And you can see that the highest intensity region of the flame is marked where the porous media is the brightest. So right now we have the flame, and the experiment that we're running is to see the effect of spacing between the discrete porous sections on the overall combustion chamber process. So we can see right now the flame is processing and jumping through the discrete sections, and upstream we made it so that the sections are wider, so you're going to see the flame move at an advanced rate. So now the flame has settled at the upstream-most section. We're running at a very rich mixture right now, so that's forcing the flame to operate upstream. So right now the flame is going to stay there for probably about an hour or so while the burner saturates with heat. And upon doing so, the flame will come out of the inlet section and find an equilibrium point within the combustion chamber. So this is our actual burner design. This is the complete section. This is noting the heat exchanger that we showed you before, the vaporization chamber, mixing chamber, and combustion chamber. Just to give you a point of reference, the maximum dimensions of our burner are 32 inches long, 18 inches wide, and 8 inches tall. And for a sense of scale, we're flowing about 45 liters per minute of air. And during the startup phase, we're flowing methane to preheat the system. We're flowing about 3 liters per minute. And then we're going to flow about 40 milliliters per minute of kerosene once we've heated the burner up effectively.
Okay, I'm going to spend a little bit of time talking about some of the operational results for the burner. What we have here is a contour map indicating the centerline temperature of the combustion chamber with respect to time. So we have on the image of the left thermocouples labeled 1 through 8. We also have on the vertical axis of the contour plot, which might not be as clear to see, but 1 through 8 corresponding to those thermocouple probe locations. We also see on the horizontal axis time. So for time equals 0, on the very far left of this plot, we have the startup phase of the burner. And you notice that the highest temperature, around 1100 degrees Celsius, is located around thermocouple port 2. You notice that as time advances, the location of the flame progresses downstream till it's located around thermocouple ports 7 and 8. At this point, we see very little changes with temperature with respect to time. So as far as the combustion chamber is concerned, we've reached steady state operation. We have great implications with this next plot as it shows us the inlet temperature of the vaporization chamber with respect to time. And since Anthony had mentioned we operate with both methane and kerosene, the methane is essential because it heats up the system. So our indicator for the time frame when we can transition to kerosene is marked by the increase of temperature beyond the boiling point of kerosene. So once we satisfy this criteria, we can then make the transition from gaseous methane to liquid kerosene.
So in conclusion, a burner was created utilizing porous media to recirculate heat from combustion. A heat exchanger was used in order to recycle heat to allow for vaporization of liquid fuels. And the burner is capable of operating off of both liquid and gaseous fuels and has potential applications in water sanitation and space heating.
And as a last note, I'd like to give a special thanks to a few people. First and foremost, Dr. Nina, our technical advisor, Dr. Vasu, our secondary technical advisor, Tim Lindner, the MIA machine laboratory specialist, Dr. Bafsar, our faculty advisor, and Dr. H, our secondary faculty advisor. As I previously stated, and as you can see, we have future in research and commercial applications. So if you guys have any burning questions, please come and see us out at table 23.
Our next presentation is called Trash Talk, Wirelessly Monitoring Trash Levels Using Solar Power.
Good morning, everyone. My name is Jaquan Hodge, electrical engineer major, and today we'll be discussing Trash Talk. What is Trash Talk? Trash Talk is a fully customizable centralized trash detection system in which various different trash cans can detect their own trash levels and send that information back to a home server, which can be easily deciphered and usable for users who want to see what's going on. It would also decrease unnecessary manpower in terms of collection, trash collection. How so? Various different companies and organizations, with our very own UCF included, aimlessly send workers out to various different trash cans to visually see if the trash cans are full or not. This wastes a lot of time and a lot of money sending these people out there. And since they make a trip to those locations and the trash cans are either empty, halfway filled, or whatever the case may be, they still empty it anyway since they made a trip there. Our system will allow them to see exactly what trash cans need attendance to, what they need to do, and they'll send the appropriate amount of people out to those trash cans, respectively. Also, our design will also cut costs of trash collection. By doing so, we're doing financial analysis with the Land and Natural Resources right now, with the University of Central Florida to make sure everything's going according to plan, and we'll get numbers in the future to let you know exactly how much money we can save. And also, our system will allow for compilation of usable data for future reference. So companies can come to their data sheet, reference all of the information that they have in front of them, and see exactly what patterns they may notice, and they can send the appropriate amount of people to those locations which trash cans need the most attention. Our Trash Talk is designed to eliminate the use of trash cans liners, but it's very customizable. So in the case that you may still need to use the liners, you can still do so. It's very adaptable to any situation you may have. We can use it for outside receptacles as well as inside receptacles, and use it for all various different kind of trash cans. So it's very customizable and it's easily usable for anybody who wants to use it. Trash Talk application. This is our very own UCF campus. This is the operation of the system, how it will work. A user can come and see exactly what trash cans are filled or not, and it gives them the status. Red is completely full, green is good, it's empty, and yellow says we need maintenance. So as a user, you can come to your system, look at the visual aid, and see exactly which trash cans I need to go to and allocate the appropriate amount of people to go to just those trash cans and nowhere else.
Good morning, my name is Ron Lasser. I'm an electrical engineering major. Now, as Jaquan said, we're using a trash salt system, and this is a little bit of how the system is going to come together. It's primarily powered by 4 to 6 AA batteries, which are continuously recharged by our solar panel, which gives us that green effect. In the event that the batteries cease to function, the solar panel can also take over power and continue to power the entire trash can system. This is linked to our motherboard, which is comprised of our microcontroller and our XB communicator, which allows us to have wireless communication to the home server. And all of the sensors, which we have a depth measurement sensor and 2 planar sensors located in the trash can, are all connected to the motherboard. The sensors detect what level the trash can is. They send this information back up to the microcontroller. It's wirelessly communicated, hops across the network to our centralized control system, and the user can update a web page and see exactly the map that Jaquan just presented. Slide. So as I said, the sensors will have a sensor that's mounted on the top, centered on the trash can, facing down, and on the rigid can liner, we'll have 2 infrared sensors at the 100% and 50% level. Slide. So the 2 types of sensors that we'll be using are a Parallax ultrasonic sensor and a Sharp infrared sensor. The Parallax ultrasonic sensor is our depth measuring sensor. We chose this one because it's really accurate. It has a higher range than the infrared sensors. It measures up to 3 meters, which gives us a good scalability, so you can use it in different heights of trash cans. It's also really inexpensive. It was only $30. And it accurately detects most materials. The only thing it has a problem with is soft materials because it uses ultrasonic pulse, which gets absorbed by the soft material. The Sharp sensor, as I said, will be our planar sensors, placed at 100% and the 50% level. And this one has a range of up to 80 centimeters, which is not too long, but it's good enough to see that something has breached the plane. This one is extremely accurate, the digital version, but it doesn't work too well in sunlight. So that's why it's placed inside the trash can where it's out of the range. Also, the ultrasonic sensor, based on the testing, is the recommended sensor for any application because it functions the best in all types of environments. Slide. So this is basically how the ultrasonic sensor works. It sends out an ultrasonic pulse, it hits the nearest object, and the sound is reflected back into the sensor, so it lets it know exactly how far it is by using an equation that involves the speed of sound in air. Slide. Common applications of ultrasonic sensors are in hospitals and ultrasound machines, and ultrasonic sensors are the basis for sonar technology, which you see on ships and submarines. Slide. The infrared sensor works exactly the same way as a ping sensor, except instead of ultrasonic pulse, it sends out an infrared beam. The beam is reflected back and it returns a voltage, which lets you know how far away the object is. Some of the common applications you see are paper towel dispensers in the bathrooms and also the safety sensors that you see in most garages. Slide.
Okay. Good morning, everyone. My name is Errol, electrical engineering major. How does trash talk? By using the motherboard photo here on the left side of the screen, using the microcontroller, this takes the data from the trash can sensors, compiles into a packet along with the GPS data, and then sends it on to the next node, passes it on and so forth to the next trash can, till it gets to the home system where it's actually downloaded and the data is compiled and put into the program so we know exactly what trash can status is at any given time. Next slide, please. How is that done? Through a wireless mesh network. Each trash can has multiple connections to the neighboring trash cans around it. This may seem redundant, but it's actually specific of the design that if one node is broken, the data will get to another, to the home system through another link. So that actually guarantees the security and the reliability of the system through having multiple connections from each trash can to another one. So.
Hi, my name is Paula Wen, computer engineering. So when all the data comes into the home system, it will be stored and displayed on a user interface, which is a website. So the markers you see on the map are the trash cans. The red means that the trash can's full, the green means not full, and then the yellow means not, needs maintenance. The user can then log in and be able to edit the system. They can add a brand new trash can or remove one if they need maintenance on it. And that means like our system will be scalable. You can add trash cans or remove them however you want and display them anywhere you want.
Power supply. The power supply that we're utilizing is going to be using, as we said earlier, both 4 AA rechargeable batteries or more, depending on how big the system may be, as well as a solar panel. We have a redundancy system in which if the batteries, in some cases, were to fail, as Ryan said earlier, the solar panel would take over and charge the system continuously. We want our design to be able to last without any human interaction for as long as possible. So we have our system set up to last, on minimum, 8 months by itself without any problems. This is just going to be a representation of how the system will actually work and come together. We'll have the solar panel charging the batteries directly. The batteries, in turn, will be charging the system, the trash can, and allowing it to work appropriately. In the case that the batteries stop working for some reason, one of the batteries busts, something happens, they just malfunction, we'll have our system automatically switch over to the solar panel supply and continuously charge the system, which hence making it self-reliable, self-sustainable, and allowing the system to last as long as possible without any human interaction. A summary of what we briefly just said. We just discussed everything that we were talking about. We're currently still in the process of a financial analysis with the Land and Natural Resources at UCF to figure out how much money we can actually save the university or other companies who will utilize our system. Our future application would be other college campuses as well as residential areas, hospitals, big city parks, and theme parks. And it's also endless. We can use it anywhere else we feel is capable. It's very scalable and it's very usable in all situations, so it's very customizable, as I said earlier. If you have any questions, you would like to come see our project, we'll be right outside the door here at table 17. Excuse the mistake.
Thank you for your support.
Our next presentation is Solar Unmanned Aerial Vehicle providing rush hour information.
All right, good morning, everyone. We are Team Icarus, and our project is a solar UAV, or unmanned aerial vehicle. My name's Alex Acquel, and I'll be presenting the basis of our project. Currently, the Department of Transportation has allocated funding to several different universities across the United States. Some of the universities closer to home are the University of Florida and the University of South Florida, and with this funding, they're assessing the implementation and feasibility of an airborne traffic surveillance system, or ATSS for short. Essentially, what this system allows is it utilizes a UAV platform equipped with video surveillance systems to have live-time traffic data collection. This is an emerging market and immature, and we're hoping that our UAV, which has the surveillance equipment and a unique feature, which is the solar integration, will be a unique solution to this problem. The reason why we integrated the solar aspect into our UAV is 1, for an extended flight time, and 2, to really push that green initiative. We have 3 different components that combine together to make our project unique. The first one, as I highlighted earlier, is the solar augmented power. This will allow us to reach our goal internal flight time of 2 hours. As I mentioned earlier, green energy is huge in today's global warming conscious environment. And with our solar power and our electric batteries, we're able to utilize an electric motor, which is beneficial for 2 reasons over the gasoline one. One is noise pollution. The electric motor runs a lot quieter and is optimal for residential areas. And 2, we don't have any CO2 or carbon dioxide emissions. Our UAV is equipped with a camera, the Fat Shark NTSC, It's attached to a gimbal, which allows 360-degree surveillance. It's capable of live video stream in color and has a range of 5 kilometers. Our last aspect of our design is we designed it for portability. The first thing that we wanted to ensure was a short takeoff distance, so it could be deployed anywhere. It's capable of taking off on a 25-foot grass runway, which we proved during our flight tests. It is also capable of hand launch, which is also visible in our video that we'll be showing later. Our second design aspect are the modular wings. We have 2 reasons for this design. The first one is it allows it to be disassembled for compact automotive transportation. Essentially, you remove 4 pins and you can put our whole UAV within the truck bed of an aircraft, within the truck bed of a vehicle. And also, the reason for our detachable wings is ease of maintenance. Each of our wings feature a lightweight 1.85-pound design.
Good morning, my name is Matthew Lauer. I'm going to talk to you a little bit about our design drivers. As Alex alluded to, the main driver for our design was integrating the solar power and specifically achieving our 2-hour flight objective. If you refer to the graph on the slide, the vertical axis shows the power output between flexible and rigid solar panels that we conducted a trade study upon. The horizontal axis shows the area required. We found that the rigid solar panels, put out 3 times the power as their flexible counterparts. So to give you a little bit of scale for what we've got here, this right here is a unitized solar cell of the rigid cell. It's approximately 6 inches this way by 2 inches this way. And this right here is mounted in string form underneath our monocoat on top of our wings. So behind me is an animation of not only our conceptual assembly, but also a rough visualization for our manufacturing process. So right now is an exploded view of all of our main subsystems. So to start, we mounted our vertical and horizontal tail assembly onto our carbon fiber spar, which is shown here. This assembly allowed us to have the moment arm on the back of our aircraft necessary for flight stability. Next, we mounted our motor and our prop onto our carbon fiber spar. To power our whole propulsion system, we used 2 solar-charged lithium polymer batteries, shown here. In keeping with the modular design that Alex alluded to, we have a motor bracket, a wing bracket with the built-in dihedral and angle of attack. And also in keeping with the ease of maintenance, our wings, which are an Epler 214 airfoil design, slide in as shown there. And finally, our printed plastic fuselage cover keeps all of our sensitive electronics safe. So in keeping with the lightweight design, we had to make sure that our fabrication process was very unique. To achieve this, we utilized 3D printing out of a local rapid prototyping facility. The image on the left shows the actual 3D printer used. The image in the center shows the actual process. So each yellow rod represents an extruded piece of plastic that's layered up from the substrate, shown here. The final product shown on the right is an example that we used in our project, and it's actually our 3D printed fuselage. So shown here, and this is where our prop comes out the back and, landing gear. So as with any design project, we face several challenges and variables. The largest one was our power storage system, We essentially had to figure out how to charge our lithium polymer batteries, which are very dangerous if charged incorrectly, using our solar power. The second design challenge that we came across was tolerance and consistencies. This led to a 13% overweight estimate and a 7% increase in our original wingspan design. This required that we had to structurally reinforce our wing bracket to make sure that we maintained our dihedral.
Good morning.
My name's Aaron Trone, and I'll be presenting some of our testing and our commercial value. So here you see a H-Wheel setup that we did, which is hardware in the loop. We basically simulated a flight scenario on the ground where it's safe so that we could get an estimate of flight time. So we did it with and without solar augmentation and found that we got a 22% increase in flight time with the solar augmentation. Our commercial value. We did lots of research in this area, as Alex was saying earlier, and found that the DOT is currently funding several universities across the country in order to research the implementation of this ATSS system. We find that our product's customer would be the FDOT, as they're already funding the University of Florida and University of South Florida in this ATSS system. We've done some research and saw that the areas that we could help vehicle surveillance or incident response, emergency vehicle guidance, etc. Here will be a flight video showing Icarus. So we'd just like to give a special thanks to Progress Energy for funding us, University of Central Florida for facilitating our project. If you have any questions, concerns, you can see us at our table outside. We hope you enjoyed the Top Gun.
Or table 21.
Or table 21.